How much energy does anti-gravity really take? Have you ever wondered how much energy it would take to defy gravity? The idea of anti-gravity sounds like something out of science fiction, but let's break it down with facts. First, it is important to note that there is no established scientific method or technology that can produce true anti-gravity by negating gravity itself. This means we cannot define the exact energy cost of anti-gravity in the way we might hope. Gravity is a fundamental force that arises from the curvature of spacetime, which is caused by mass and energy. To counteract gravity, you need to apply an opposing force, and that requires energy. For instance, when you lift an object, the energy you use equals the gravitational potential energy gained by that object. This is calculated by multiplying the mass of the object by the gravitational acceleration and the height to which you lift it. This is simply mechanical work, not anti-gravity. In the realm of experimental and speculative science, some intriguing effects that resemble anti-gravity have been explored. One of the most notable examples is magnetic levitation. This technology uses electromagnetic forces to counteract gravity, as seen in maglev trains. These systems demand continuous energy input to generate magnetic fields and maintain stability. Recent experiments involving spinning magnets have shown stable levitation through unique interactions. However, these methods still consume energy to keep the magnets rotating and to sustain the electromagnetic fields. The energy cost can be significant, depending on how much power is needed to spin the magnets and maintain those fields. Another fascinating area of research is antimatter, particularly at the European Organization for Nuclear Research, commonly known as CERN. Scientists have tested whether antimatter experiences gravity differently, which could lead to the concept of repulsive gravity or anti-gravity. So far, results indicate that antimatter behaves like normal matter under the influence of gravity, meaning no natural anti-gravity effect exists that could reduce energy costs. There have been claims about devices that can shield or cancel gravity, such as the superconducting disk experiment from 1992. However, these claims remain unverified and controversial. No reproducible technology has demonstrated genuine anti-gravity effects that reduce energy expenditure below what is needed to simply oppose gravity mechanically. From a weird science perspective, strange experiments with rotating magnets and exotic particles hint at unusual forces and stable levitation, states that might mimic anti-gravity. However, these phenomena still requiring energy input to maintain and do not eliminate the fundamental energy cost of opposing gravity. In summary, true anti-gravity as a force that cancels gravity with zero or minimal energy input is not supported by current physics. Any practical effect that resembles anti-gravity, such as magnetic levitation, requires continuous energy to generate forces that oppose gravity. The energy required equals or exceeds the work needed to lift or hold an object against gravity, plus losses from inefficiencies. While strange and quirky experiments reveal novel ways to levitate or reduce apparent weight, they do not break the energy rules set by gravity and thermodynamics. So, the energy cost associated with anti-gravity concepts is essentially the energy needed to produce an opposing force. There is no magic-free ride, just clever engineering that still follows the laws of physics.